Hi, my name is Todd Rosedahl. I've worked in power and thermal management at IBM for over 20 years, working on power solutions for our, thanks Andrew, for our servers. And I'm going to talk today about managing and measuring power consumption on your server, specifically in an OpenPOWER environment. We have open source code up and down the stack, and you heard our friends from Rackspace talk about more open source code that we're trying to get going. So I'm going to talk about the techniques you can use to manage the power and measure the power. This is the data center there. All right, so you can read these fun facts, but it's clear that throughout our data centers, we're using more and more power. You just saw the keynote, if you did, and every time he talked about performance, he was talking about performance per watt. He was talking about how can we reduce the amount of power we're going to use. There's a smaller little GPU coming out using only like 40 watts. We have to go after keeping this power down because it's so intimately related with the performance that you're going to get on your servers. Let's talk about this ecosystem. This is the open source ecosystem that's been enabled. Here we have all of this has been open sourced. We're going after the firmware down here and the hardware. We're going to open source that. Everything in green here has been done. So Opal is that OpenPOWER abstraction layer. That's been open source. There's the host boot code. That's our BIOS that loads and gets your system initialized. And then newly is this on-chip controller. I announced last year at this conference that we'd open source the OCC. And so that's I'm going to talk about that a little bit more. And then there's something new called Aimster. It's a tool that you can use to do detailed profiling of your system. You can get in and analyze the power and performance profile. And so that has now been open sourced as well. And so you have the ability to do much more detailed analysis. So next is a video that talks about the OCC functionality. I think. No? So there's no sound. Can we get sound on this?
Processor frequency and memory bandwidth. This enables customization for performance and energy management, as well as system reliability and availability. One of those customizations is the ability to monitor and control the processor frequency. Here we show the system starting out with the processor running at the nominal frequency and all power and temperature measurements within acceptable system parameters. The processor frequency is then increased above nominal, which causes the system power usage to increase and the processor temperature to rise. Here we have it set so that as the processor temperature approaches the maximum limit, the OCC reduces the system frequency slightly to ensure that the system stays thermally safe. Another customization available is power capping. Here we see that as the workload on the processor increases, the system power usage increases. As this power consumption approaches the power cap limit, the OCC will reduce the processor frequency and allowed memory bandwidth to keep the system under the power cap. When the system utilization is low, the frequency can be reduced to reduce the overall system power consumption. The OCC responds quickly to system fault conditions in order to keep the system running. In this example, a power supply has failed. We see the total available power drop, and the OCC lowers the processor frequency in order to enforce the new, lower power cap. With the open source OCC code on OpenPOWER systems, the system management functions shown in this video can be implemented, enhanced, and expanded. Additionally, new, innovative functions can be created. Whether your solution demands power savings, thermal protection, or maximum performance, you now have the right tools and the control to strike just the right balance between these three attributes.
All right, so that video describes overall what the OCC does. One, it is a separate 405 processor right on the die with the other cores, and I'll talk about that further on or more later, but the key there is that it's not taking any performance away from your server. All the cores are still there for you to run your customer jobs. And this picture is just showing that all the fingers really that the OCC has. It has fingers in many different pies here. So it's talking to the processors and getting their temperatures. It's talking to the memory. It has an interface up to OPAL, talk back and forth to exchange information so that we can better tune the system. All the hardware. So it reads the power of your system every 250 microseconds. So because it has the ability to access all that data, it can do these functions here. It can do the power capping and the performance tuning. And then today I'm going to talk more about the sophisticated measurement and profiling it can do. It has all that data, and now we're going to be able to export that data out for use by some tooling, so you can do some profiling and figure out the power performance trade-offs. So another view again of the OCC. This is the P8 module. And of course, I've blown up the OCC for effect, but you can see it's right here on the die with the other cores, and it has access to that power bus. That's the main fabric bus of your system. Because it's on that bus, it can do anything. It can talk to main memory, so it talks actually to the other OCC via main memory. It talks to up to the OS through main memory, and then it has I2C interfaces down to the BMC, which we just had a rack space talk about the BMC. It's giving information to that BMC about the temperatures and the powers, so it can export that out via IPMI, and it also, the BMC uses that information for fan control to keep the system energy efficient. And it has SPI interfaces to some special power measurement hardware, so that's how it can read every rail, every voltage rail, and the total system power. It can read to do the power capping. All right, so I should point out the way this works. The standard Linux governors that you'd be used to using with any Intel system, those are still in place. You can have performance, that's on-demand governor, the balance, the power save. Those governors work, and they still set the frequency and say, here's the frequency I want the system to run at. The OCC is just there to enforce power and thermal limits to make sure that we don't go over power or over temperature. Also, we do have the idle states, just like the Intel systems. So we have nap, sleep, and winkle that shuts off. We shut off clocks. We turn off clock and cache. And that's really a great way to save power when you're not using your processors at all or for a period of time. There are 3 different power caps supported. You have a regular system cap. You have some emergency cap. In the example in the video, it was used for if you lose a power supply. But it can be used really for anything. Since this is all open source, you can change this to do whatever you want. With that, you can have it if a battery goes low, or however you would decide to use that second power cap. And then there's a third one, so DCMI is supported. That would be like a customer or user cap. That cap gets sent from the BMC up to the OCC, and then it'll enforce the lower of the 3 caps. There's a little bit more about how this voting box works. Here's OPAL again. So OPAL and Linux above it is actually saying, here's the P state I want based on the utilization that they see. The OCC is here reading this power every 250 microseconds from that power measurement hardware, and then making a decision based on those power caps. Say, is it okay for OPAL to set that frequency, or should I clip it? Similarly, we have the temperature control down here. There are 4 DTSs on every core. The OCC is reading those, averaging them, comparing it to other limits that were set in the system to say how hot my memory should get, how hot should my processor get, makes a decision, and then also decides what is the maximum P state I'm going to allow this system to go to. So the desired comes in, gets clipped by the maximum, and then the OCC hardware takes care of automatically setting the voltage and the frequency. That same data that was used, that was collected by the OCC, goes down to the BMC for its use for either the fan control or export. All right, so here's sort of the new thing for this year is this measurement. So you can measure a system a number of ways. And traditionally, you would go in band to the OS. You would get performance information. You can get some power information that way. That's good for some things. It has tighter workload synchronization, right? You start a job, you can go, exactly when you started it in the OS, and you can read the data that way. The bad thing is it's using the system processors. You don't really want to use your system processors to measure a system because you can affect it, right? So the other way to do it is go out of band. So if you go out of band here, this is going through the BMC. The standard IPMI sensors are supported. So you can get all your temperatures, inlet temperature, processor, core temperatures, as well as power from every rail. DCMI is supported, which gives a little more flexibility for reading that power. The new thing here is Aimster. That's been open sourced. And so that is a pass-through, an IPMI pass-through interface. So the only entities that need to understand this complicated set of instructions is Aimster would be running here on your laptop, and the OCC itself would understand these commands. The BMC is just a pass-through here. So a command could come down through that BMC to the OCC and say, measure something in some fine-grained detail. Store that then in OCC's SRAM, and then grab it out for analysis. More details on Aimster. It stands for Automated Measurement for System Temperature and Energy Reporting. Again, it's a pass-through, so it goes down in through this. This would be your BMC into that OCC. And the way it works is it has an 8K buffer. Since it's been open source, you could change this to whatever you want. You could have a scrolling buffer, but today there's an 8K buffer. And what happens is that you would tell the OCC, put some particular data into your SRAM. So you would maybe take that 250 microsecond power value that's being read, and you could log that every 250, log that up in main memory. Then you would get 8 full K of data. Then you go read that, and you can export it, graph it, and then that way see what happened with the power. Or you can do something on a slower time scale. Here I said potentially a temperature sensor. 2 milliseconds is even too fast for a temperature sensor, but you can read a temperature sensor, but much more slowly, and then you get a total of 8 seconds worth of data. But again, it's constrained by an 8K buffer. So it fills the buffer up, then you read the buffer and post-process it. This is a description of the sensor. So when I say a sensor, we have a particular format. This is up there in main memory or in our SRAM. And so there's a sensor name, of course, and there's metadata. There's data about the data. We say like how often this particular thing is updated, how often it's read. There's a minimum and a maximum that are stored for every sensor over whatever period of time. And then there's an accumulator, which is a key aspect. So we can continually be reading the power. And we're updating this accumulator. So you can read it once, you can read it a second later, and then you can see the difference, how much power was expended during that time. And that way you can get an energy total, and you don't have to say reset this sensor. It's just always accumulating. This is a sample sensor list. There's a full document out there that's been open source that describes these sensors. I'm just giving you sort of a feel for what you can do. So you can get all the voltages. You of course have the frequency of your core. You can measure that. The utilization, the instructions per second, all the temperatures and powers that I've described. So there's a rich set of utilization and so performance and power data you can access to correlate between those two things. And here's a simple example, very simple. So we were running along and had a workload running. We shut this workload off, or really probably winkled this core. Completely stopped the power, brought it down to 0. We were also monitoring the temperatures of the various cores in the nest as we went. As soon as we dropped that power and turned that workload off, our temperatures dropped. You would expect this. There's nothing novel here or new, but if you use this type of data, you could find anomalies in power and utilization. So some of the insights we saw, and this is also what was just stated in the keynote, is you have to visualize these things. Looking at a string of data is not going to help you, but if you take that data and you graph it, and if you're very careful in making sure you're time aligning your sensor data correctly, so you're looking at things in the same time frame, you can really see a lot of interesting results. And we've seen issues with voltage slewing. We've used this to tune algorithms to get better performance per watt. It's all really about performance per watt, right? You want to be able to tune that exactly to get to that maximum performance per watt, and you can do that using this tool. Okay, and then just another plug for the OpenBMC. All this stuff I showed you before, it's all open source. That BMC is not, right? But now that Rackspace was just up here, they said, hey, we're working on this OpenBMC. There's a session on this tomorrow as well that if you're interested, you should attend to get more detail on how you could contribute and benefit from the OpenBMC. Just a series of references. There is so Aimster's been open sourced. This BMC's been open sourced. Also, there's a document out there. If you don't want to use Aimster, there's another method you can use. You can just do your own IPMI commands that pass through the BMC, and there's information on exactly how to do that out there. All right, that's it. Thank you.